All right, 5.2 starts talking about definite integrals. We were talking about using RAM for rectangular approximation for area under the curve. Now we're going to refine our process a little bit and try to get something more accurate. So the first thing we need to do is review sigma notation. So you remember from advanced math we talked about sequences and series, and we did a little bit of sigma notation, and what that is means this note thing needs capital sigma, Greek letter, and it means the sum. And we're taking terms from 1 to n, and this is the term. So that means we're adding up a1, a2, a3, a4, a5, a6, all the way up to an, whatever n happens to be. This is a finite sum because it has an end. It stops somewhere, and we're adding all those up. Now in calculus we have something special called a Riemann sum. Riemann sums are really important because they help us with our integrals. And what it is the function value at each of these little places times whatever the delta x is between the places. Now, a RAM is an example of a Riemann sum. What did we do? We took the function value, let's say we were using midpoints. We took the function value, so this is if this is our, let's call this C1, we'll call this C2, and this place C3. So this is our function value at C1, and this one's our function value at C2, and this one here is our function value at C3. And we multiplied it times whatever this delta x was, whatever our space was in between. Now, we were using equivalent spaces between for each rectangle, but what this tells us is that we don't have to. This equals the function value at C1 times whatever that first delta x is, plus the function value at C2 times whatever that second delta x is, and so on and so forth until you get to the function value at Cn times the delta x n. And what that means is we can use different widths of rectangles and add it all up. And this is just the area of a rectangle, right? Length times width. And we're adding it all up. So this is the notation called a Riemann sum to show us what we did. Now, we have some definitions and things we have to go over. If f is continuous on a closed interval from a to b, then we can use the Riemann sum. And our ck that we talked about here is some point between an x value before that and an x value after that. And then our delta xk is the length of the kth subinterval. So just like we said here, our delta x1 would be well, I guess I should say width would be an easier way to put it, right? A width for that first subinterval would be our delta x1, and so on and so forth. Subintervals in some portion of this part where we're continuous from a to b. Okay, remember, they're not always the same. In RAM, we use the same. Our delta x would be the same for every single one, but we don't have to. So let's look at a picture here. Let's say we have a function like this, and we want to put some rectangles in it and figure out what the area is. So we'd have rectangles here for using midpoint Sorry, it's hard to draw straight in this pad here. All right, if we have this, you have to be really conscientious about making sure you pay attention, because this here is going to give you a negative area. And this here is going to give you a positive area. Why is that? Of course, the function values here are negative, so our delta x's are all positive, but our function values are negative. So this one's going to give you a negative area, and this one's going to give you a positive area. So you're going to have to pay attention to that and pay attention to what the question is. Because if we want to find the total area, then this, we would just calculate this and add it up as it is. But if we want the net area, then we're going to have to calculate the area above the x-axis and subtract the area below, which means you'll add a negative. So that we get the whole area, this and this added together, their net area. So you can take the absolute value, but you have to pay attention that you're going to have to look at these graphs and see if they cross the x-axis and figure out what you're looking for. All right, so let's look at this. Now, we used limits to make a definition for derivatives, so we also can use limits to give us a definition of an integral. Now, your book, we're going to call this maximum delta xk. That's our maximum width. Your book calls it this funny looking p thing. The norm of the partition is what your book calls it. But what it is the maximum width of these rectangles, because our area under the curve, as we get, remember we talked about more and more rectangles, gives us a better and better approximation. So what we want to look at is the limit as our maximum width here goes to 0. Because what happens if we're getting more and more rectangles? That's right, our widths are getting smaller and smaller. So even if we don't have all of them equal, we look at that maximum width and make sure that it's going to 0. Now we use those Riemann sums that we were talking about because we're doing these rectangles. So we take this sum of all these rectangles, the area of these rectangles, this Riemann sum, and take the limit as that maximum delta x goes to 0, so that we're having these skinnier and skinnier rectangles until we get all the way to the point where we have an exact value. And that is I, we'll call that I. It exists. So we say if this limit exists, then f is integrable on this interval from a to b, and I is called the definite integral of f over this a to b. Now, if f is continuous, then it is integrable. Okay, we don't have as many restrictions as we do with differentiability. The integral, it is integrable if it is continuous. Now, so we know that we're looking at this going to 0. Now, let's think about this a little bit. You can also write this a different way. We could write it as the limit as n goes to infinity of this sum, because what does that mean? Okay, here we're talking about the limit as the widths get smaller and smaller and smaller, and here, what are we talking about? Right, the limit as we have more and more rectangles. Okay, now, if we take this k out of here, and we're using a constant for that, we can use our delta x as b minus a over n. Okay, that's usually how we're going to do it. We're most often going to have even spaced, like we talked about when we were doing RAM. All right, so how do we write all this in integral notation? Well, we have our limit, and what we write is, this is an integral sign. We're taking the integral from a to b of f of x dx. So this is our function. It's called the integrand. And this tells us our variable of integration. These are our limits of integration. So we take that Riemann sum, and we take its limit as n goes to infinity or as the delta x goes to 0, and we end up with an integral, just like we took the limit of our difference quotient, and we ended up with the derivative. Now, the definite integral is a number. When you calculate this out, you will get a number every single time. It is the area under the curve between A and B, period. It is a number every single time. So you need to make sure you remember that. So let's look at an example here. If we take the limit as that maximum delta x, or as your book calls it, this norm of the partition. So this is the same thing, remember, as our maximum delta xk. The limit as that goes to 0 of k equals 1 to n of ck squared minus 3ck delta x k, where p is any partition of -7, 5. Okay, so what is this saying? This is saying we're making rectangles from this function with this width along our x values from -5 or -7 to 5, and we're making them smaller and smaller so that we can get a good area. So how do we write this as an integral? Well, the way you would write it as an integral, we're going from -7 to 5, and this gives us our function. It's x squared minus 3x, because remember, this is f at ck in our Riemann sum notation. And then we're taking, just like with derivatives, the capital delta gets smaller and smaller and becomes a lowercase delta, which we just write as a dx. All right, so the area under the curve looks like this. Now remember, you have to take that into consideration, whether it's above the curve or below the curve, and you'll have to split it into parts to make sure that you're getting all the area depending on how it's going to work. So we'll talk about this some more. We'll do one more video for this section since this one's already gotten kind of long, and look some more, but mostly right now what we just need to look at is the notation. Make sure you know those Riemann sums and the limit and what that means.